Yeah.
All right. So on Monday, didn't have a lot of people join, but that's okay. It's fine as long as the video is out there. So I went over more about dummy variables or 1-0 variables in regression. So I talked specifically about what happens if we have a variable where we've got more, like kind of a qualitative variable where there's multiple categories and we have multiple indicator variables. How do we deal with those situations? It's a good one to know how to work through. And then the other thing I talked about was what do we do when we have a dependent or a y variable, left-hand side variable that's only 1-0. And basically the interpretation of our coefficients, instead of being like the increase in the units of a y variable, well, now if our y variable is 0, 1, it's an increase in the probability that we see this thing occur, whatever the 1-0 variable is. So that's kind of what I covered through there. I'm going to skip around the slides that were up there, the week 14 slides. Kind of had for last week, but we're going to just use them this week as well, kind of continue to work through them. I jumped forward a little bit. So there's some things in there like, I think it's differences in slopes. We're going to skip all of that until we get to this slide that says log model. Okay, so what is this slide? 27. So one thing that we might have, let's see, hopefully this doesn't freak out. Okay. Awesome. One thing that we might have is that the relationship, whatever data we have, right, maybe doesn't have a real linear relationship, and we actually want to allow that relationship to have some curvature to it. Okay? So one issue that we have with really large values, and we start to think about, maybe this is something like GDP or some crazy high values for income. Maybe we're more concerned with percentage changes, right? So maybe it's that we want to know what's the effect of a 10% change in wages or a 10% change in GDP. And so we want to allow kind of the slope not to be necessarily linear, right? And kind of account for this. So what we can do is use the natural log of different values to try to capture the fact that these relationships aren't always linear. Okay? So the log model, what we're really going to do is take the natural log of both our original x and y variable. Excuse me. Then our coefficient, let me see if I have, yeah. So let's say I take the natural log of x and the natural log of y. Right? So the interpretation now becomes, instead of a 1 unit change in x causing a 1 unit change in y, or beta, sorry, unit change in y, it's going to be a 1 percentage point change in x predicts that the y variable goes up or down by whatever beta 1 is percent, right? So if beta 1 here was like 5, then it would be a 1% increase in our x variable. We predict that our y variable goes up by 5%. Right? So it changes everything in from what we would say like our levels or units to looking at only percentage changes. Okay, so this might matter if you think about, let's say I see a wage increase from $40,000 to $50,000, right? So the $10,000 increase, right? And maybe I want to know what's the impact on, I don't know. I don't know. I can't choose a 1-0 variable. Maybe the debt that the person has, right? That's how does a $10,000 increase in income impact the amount of debt that person carries for the next 10 years or whatever the measure is. Well, that $10,000 change in wage is probably going to have a much greater effect than if I was looking at someone who's going from making $250,000 to $260,000, right? So the same change in income, we think probably has different effects depending on what it's like relative size to where my baseline is, or the percentage change. So 1 to 2, right, should be treated differently than going from 10 to 11, even though it's the same units. So we take the natural log. This then, we could look up the mathematical proof, but taking the natural log essentially changes everything into percentages. So instead of 1 unit increase, it's a 1% increase in x1, causes a beta 1% change in our y variable. So we can kind of think about this in the context of different examples. So I'll start with this example where I think about the relationship between height and weight, right? So I know that as someone gets taller, like they just, even if they have the same muscle mass and everything, you would just have to weigh more. You have more bones, you have more of your organs, I guess. I'm not an idiot. I didn't say more organs, more of your organs, right? Like everything's larger, right? So we know that as height goes up, weight is also going to go up, right? And then it might not be a linear relationship, right? If I'm going from 5 foot to 5'1", maybe that has a much bigger change on my weight than if I'm going from 7 foot to 7'1", right? So I know that maybe I want to capture percentage changes, so I could take the natural log of height and the natural log of weight and look at that relationship. So I've got this height weight relationship I'm thinking about, but I don't want to treat every inch increase the same. I want to look at percentage changes. So I just take the natural log of each one of those variables. Okay? Once I have the natural, and if you think about this in Excel, like this is just creating 2 new columns, right? Taking the natural log of X and taking the natural log of Y. Okay? So I run this regression, and here's the output I get. So I believe on the left here, I have kind of the more traditional, what we've seen already, which is just the levels. We would call this like a level model, where I haven't done anything to the original data, just looking at the data in units. Then I have the natural log, the log model, right? So now everything's in percentages. That output's on the right. So notice, just by including height, I'm explaining about 20% of the variation that exists in weight. Right? So for every 1 unit increase in height, or for every inch taller a person is, we expect their weight would be about what, 4.7 pounds heavier. Now, and this is very significant, right? The p-value is basically 0 here. Now, I'm only explaining 20% of the variation that exists in height by using weight, but this is a naive regression. I'm not adding in a bunch of additional controls yet, because I really want to focus on the difference that we see if we instead change this to a log model. So now how would I interpret my coefficient? Well, now it would be, if height goes up not by 1 inch, but if height goes up by 1%, the expected increase in weight would be 1.7%. Right? So it's kind of interesting, or at least to me it was, I guess. But like for every additional inch, it's not like a 1-to-1 kind of weight gain. It's actually like you see almost twice as high of a percent. No, not twice, like 1 to 1.7. But I'm getting closer to, right, adding almost twice as high of a percent to my weight from an additional 1% increase in height. Does that make sense in terms of the interpretation? Any questions on that? Now, once again, it's a little bit different test statistics. The p-value is a little bit different, but it's still so high of a test statistic. Our p-value is still about 0. So we would say that this is very significant, right? Significant at all levels, right? There's a very significant relationship between height and weight. This is somewhat intuitive, I think. What's more interesting, though, to start to determine, okay, so I ran these 2 regressions. Which one do I use? Which one is more valuable? Which one is able to predict weight at a more accurate kind of level? Well, we're going to use our R-squared to compare these 2 models. Okay, so by simply including height, I was explaining 20% of the variation in weight. However, if I change the relationship to allow for percent changes and kind of this non-linear relationship, well, now I'm explaining about 22% of the variation, right? So we can kind of think about this model is maybe explaining a little bit more of the variation that we see in that Y variable. So it's probably a little bit better at predicting kind of changes in weight from different percentage changes in height. Okay, so we're going to use the R-squared to determine what model is better. Here, the log model appears to be a little bit better than that level model. Okay, so we explain a little bit less variation here. So we can actually, I already went through all this. So we've got that coefficient interpretation. You can kind of think about, there's a lot of other ones. Usually it's things that are going to have a lot higher values, right? Where I could say, like the income, right? I can see incomes between 10 and 20, and then I can see incomes to 200 to 210,000, right? So revenues, incomes, populations that are pretty large, and then we have some small populations as well. units sold. Some companies have a very small quantity sold, and other companies, I mean, you're talking in the millions, right? Prices, if you look at the price across different goods, I mean, I can see prices as low as 10 cents and as high as, I don't know, take the most expensive like good you can think, or if you can think of. So a lot of the times, especially with dollar amounts, we'll want to use percentage changes. Now, one problem arises. I could start to throw in other control variables, and I could start to look at the relationship between other variables and weight. But what if I included an independent variable and I wanted to use a log-log model? And maybe I'm thinking about something like, oh, I know that there's weight differences between the two genders on average. So maybe I want to add in what's the impact of being kind of, whether or not I make the gender variable male or female, what's the additional kind of change in expected weight or predicted weight from that? Well, let's say I want to analyze that relationship under a log-log model. What's going to be the problem? You have a calculator. You know where your natural log value is? Can you take the natural log of 0? Yeah, so it'll be 1. So the problem with these 0, 1 variables is you're always going to have one there. Like you don't have any variation, right? Once you take that natural log, it's not changing your results at all. So it doesn't make any sense for us to use log-log models when it comes to analyzing the relationship for indicator or dummy variables, right? So we really only want to use it when we have a nice continuous variable, right? Or at least close to continuous, right? It could be only integers, but at least it has like no maximum or anything like that. So it doesn't really make sense for us when we're looking at dummy or categorical variables. We wouldn't want to use the natural log there, okay? All right, so one nice thing about this log-log is it's talking about percentages, right? So, I try to relate this maybe to other classes, things that maybe you want to forget, or maybe I don't know, maybe you miss those days. So let's say I had this log-log specification. If I remember from Econ 201, these things called elasticities, right? So this is the percentage change in price over the percentage change in quantity, right? Well, if I'm thinking about elasticities, what if my percent change in quantity was just 1? Right? So I'm interpreting it as like there was a 1% increase in quantity, then my elasticity would really just tell me that percentage change in price. So if I come down here, if I think about, let's say I set up a regression where I've got, and actually I think what I wanted here was, oops. So I could set up, I'll actually set this in reverse. I think this probably makes more sense for 201. Or actually, no, I do want this to be here. What am I thinking? So let's say I set up this regression, right? What I can interpret this as is a 1% change in price would start to predict different changes in quantity, right? So how responsive are consumers being to different percent changes in price, right? So this log specification is really going to give me things like elasticities, because the interpretation is just always 1%, right? A 1% change in that X variable tells you the percentage change in the other variable, right? So you could do cross price, you could do income elasticities if we wanted to do, income and quantity. And so we see these log models used quite a bit, right? Especially in economics, right? We want to get some elasticities. So the other two types of models we can use are kind of the mixed combination, right? I can do a log level or a level log model. So a log level or a level log, kind of the first one, right? This first name or term, that is applied to your Y variable or your left-hand side variable. The second term or the second name refers to what you're going to do with your X or your right-hand side or your independent variable. So a log level will look something like this. So let's just kind of keep running with the height weight. Right? A log level would be I take the log of my Y variable, but I leave my x variable alone. Right? I leave it as units, the levels of it. Okay? And then for the level log, well, level, that first one refers to my y variable, so I leave that alone. But then the log part, I'm going to take the natural log of height. I think I'm writing log here, but I have to get it on your calculator, right? We're taking the natural log here. So I've got two models, all right? And the interpretation of the coefficients gets a little bit trickier. Okay? So for the log level model, where I've taken the natural log of my dependent or my left-hand or y variable, beta 1 now is a 1 unit change in x would predict that the percentage change in y would be beta 1 times 100. So beta 1 is kind of giving you, it's like the proportional change, right? It's giving you the percentage in decimal format. So if that's telling me the percentage change in decimal format, how do I get that to be a percent? Well, I multiply it by 100, right? So if you only have the level of your x variable, you don't take the natural log, the interpretation always is, a 1 unit change in x, right? If I haven't taken the natural log, then it's just a 1 unit change in x causes y to change by beta 1 times 100 if I have taken the natural log of y. Now, if I have the reverse, where I've taken the natural log of x, but not y, or the natural log of my independent variable instead of my dependent, well, now it's the effect of a 1% change, right? Taking the natural log, changed it into percentages. So the effect of a 1% change, but now I'm going to have to divide it by 100 because now it's giving me the effect in percentages, but I want kind of more like the units, right? So you can think about it that way. So a 1% change in x causes the predicted y to go up or down by beta 1 divided by 100 if I've got a level log model. Okay. So you have to treat them all a little bit, interpret them all a little bit different, right? But we can determine which model we use essentially for the sake of this class. What we're going to, there's some more complicated issues we could dive into, but for what we're going to learn and the concepts I want you to know, we're just going to look at the R squared. And whatever model has the highest R squared, we said that fits the relationship between these two variables the best. So I'm going to run each one of these models, right? So, oops, do I not have them in here? No, I have them in an Excel file. So let's do that here real quick. I have a log models one. I believe this is looking at SAT and GPA data. So we probably will have time today. I'll probably just go through two different examples. The other one that we had, and for some reason, I don't know where I put them, so I'm gonna have to download this. I think I accidentally put them on my desktop and not my Google Drive. But I've got the height, weight, and the log models Excel files up there on Canvas under the in-class data folder. So let's look at this height, weight one first. So I already had all of these regressions run, but I'll kind of show you how I would do this. So here, this sheet one, I probably should have renamed it to something like, here is kind of my original data. And then I've got a lot of observations. One thing that makes it easy instead of scrolling, right? Control Shift or Command Shift on a Mac. If I just hit the up arrow, it's going to send me all the way to the top right away. Right? So notice here, the original data I had was actually just height and weight. What I then did was create two separate columns. Oh, come on. There we go. Where I use this ln function. This is just taking the natural log of whatever value I have over here on the left-hand side. Okay. So I'll hit enter. I'll do the same thing for height. Now, if I didn't have this already created ahead of time, like for individual assignment, once I do it for that very first observation, just notice I forgot to zoom in on this, so you guys are probably squinting. All right, so once I do this for the very first observation, if I click on this cell until I get this black like plus sign and I double left click, it fills it in all the way to the very last observation for me. Okay. So it's kind of a nice little shortcut there. So now that I have these natural logs, I can do like things like the level model, the log level model, by just selecting the variables I want to be my X and Y variables, my left and my right hand side variables. So I already showed you the results for the level, and I showed you the results for the log. From those, we said the log had a slightly higher R squared. So get rid of something, right? 0.22 as opposed to what, 0.20. So slightly better, right? What I could then do is like, maybe I look at the level log model. So the level log, remember the first term is what I use, what I do to my y variable. And the second term is what I should do to my x variable. So I click on data analysis. I go to regression. My y variable, I'm looking at weight. But if I wanted a level log model, that means keep the y variable in its units, its levels, right? So I'll select that weight variable. That's my y variable. Then for my x variable, why didn't it kick me back up to the top? Well, that was where I want to do a level log model. So I need to use the natural log of my x variable I wanted, which was height. So I'll select the natural log of height. I've selected my labels here. All right. I hit OK. And now it should have just reproduced what I had. Let's see if I did everything right on this level log sheet. Yeah, sure enough, it looks the same, right? But notice here the r squared 0.20, right? 0.201. That was the regression I had before. Not quite as effective, right? That r squared is still lower than the one I had for the log model. So far, the log model is winning out. I could then also reproduce the log level model. Once again, that would be as easy as go to my data analysis, regression. If I want a log level model, then the y variable I'm using is actually the natural log of weight. And if it's a log level model, the or the x variable I'm using, will just be height, right? So it's just a matter of making sure that I'm kind of matching up whatever that model type is. Hit enter. Sure enough, so we got what, 0.2247. Yeah, it's exactly what we had in that log level sheet. So we didn't have to recreate this. I just, for the sake of getting more looks at how we use that linear regression tool in Excel, I kind of want to go through a couple of those. So here, the log level model is about 0.224. The log model is 0.225. So the log model barely wins out, right? But it does fit the relationship between height and weight the best of those four models, okay? And that's kind of signaled by it has the highest r squared, right? So when we have this model just using one variable, right, we're able to explain 22% of the variation in our y variable of weight. Okay. Any questions on that before we keep moving here? Shouldn't be too bad. You could go through the same thing. I just put up an additional kind of example in the in-class data folder, which is I looked at the GPA data that we were looking at, and I had GPAs and SAT scores, right? I then kind of took the natural log of GPA and the natural log of my SAT scores and did some regressions there for 4 different types. So from there, once again, you could go through and do all these interpretations. So let's look at the level model, and we'll try to kind of work through these interpretations and then compare to see which one has the highest r squared. So 0.168, so 16.8% of the variation in GPA is explained by just including SAT as a right-hand side ruler. Now, we talked about it before. We know that's biased. We could throw in all those other control variables we have. I just want to focus on kind of the log stuff for right now. So we're not using additional controls. So how would I interpret this coefficient? It's just a normal level model. So the way I interpret a coefficient is it's always a 1 unit change if it's levels, right, in the x variable. So if my SAT score goes up by 1 point, the predicted GPA would go up by 0.0019. That might seem really small, but 1 point on the SAT is really small, right? In terms of like its range, the range is up to 1600, or at least I think the new one, right? There's a period of time where there was just restructured, right? Maybe even when you guys took it, I can't remember, but when I took it, it was out of 1600, right? So I think they went back to that. if I know the effect of 1 unit, right, a 1 unit increase in SAT, I could do something like, well, what's the effect of a 100 unit increase? Well, if I know the effect of 1 unit, it's just that times 100. And then that starts to make more sense. If I score 100 points higher on the SAT, that would predict that person's college GPA is about 0.2 points higher, which, you know, is a sizable change when you're on a scale from 0 to 4. Any questions on that? Is that making sense so far? Okay, so then we'll look at the log-log model. How would I interpret this coefficient? Now, first of all, it doesn't look like it fits the data very well, right? Because the R squared fell to 0.12. I think it was almost 0.17 before. So now how would I interpret this coefficient? Yeah. Yep, so when we have both of them in log, everything's in percentages. So on this one, a 1% increase in the SAT score would lead to 0.74% increase in GPAs. Yeah, so if it's log, everything's in percentages. Yep, we don't have to multiply or divide by anything. Now, what if I go to a log level model, right? So the log level model, look here, I'll zoom in. First of all, if you don't know the entire interpretation, how would I start out the interpretation? So this is where we got to be careful, right? So the change that we think about in the x variable depends on what we did to that x variable. So here, we didn't take the natural log of SAT, but we took the natural log of our y variable, which is GPA. So instead of a 1% increase now, it goes back to 1 unit. One more point on the SAT would predict that our GPA changes by 0.00075. And we know it should be in percentages, but there's a factor that we're going to need to use. If we go back, you know, there's no way that we're going to have this memorized at this point. But anytime I've got a log level model, I take the coefficient and multiply it by 100. Right? So, and I guess maybe one way to think about, an easy way to remember that you should be multiplying. If you're ever going from like unit to percent, you would want to have to like move the decimal, so you have to multiply by 100. If you're going from percentages to levels, well, then I need to scale back that a percent kind of interpretation. I need to like move back to looking at decimals, and so I need to divide by 100. So here we were going from level, right, units changes in our x variable to percent changes in our y variable. So we need to multiply it by 100. So really, I can almost think about it, it's like, for making the interpretation, a 1 point change in the SAT score is going to cause my predicted GPA to go up by 0.07. Right, so pretty sizable effect if we're thinking about this one. Okay. But I think that's something like a, what, 1% would be something like a 16-point change. So yeah. And then the level log, well, here we've got the natural log of SAT. So now the interpretation is a 1% change in my SAT score. We predicted that my GPA goes up by. Now here, I'm going from a percentage to units, right? The level log, I didn't do anything to the y variable. So now I need to like scale those percentages back down to being units. And so now I'll divide by 100, okay? So now the effect of a 1% increase in SAT scores predicts that GPAs would go up by 0.019, I guess, points of GPA. I don't know what the unit, I don't ever really thought about what the units of GPA is, but it's right on the 0 to 4 scale. So that's how we could go through each of these models, have slightly different interpretations on those coefficients. And if I'm looking here, this R squared was 0.16. I believe every other model, so this one was lower, this one was lower, 0.168 versus 0.160. So here, the level model actually captures the relationship the best. And this is probably because if we actually look at the data, it doesn't range from 0 to 1600, right? Like people aren't getting 100s on the SAT, or at least the people in this data set, we're looking at their college GPAs, right? So people that go to college aren't going to be having zeros on the SAT. So we're probably looking at a pretty tight, narrow window from, I don't know, maybe like, I'll even be real generous, maybe like 800 to 1600, right? Kind of a narrower range where the values aren't really insanely small, they're not insanely large, and so the percentage changes don't really matter as much for a variable like this. It would matter a lot more if we had something like income, where some people are making like below 10,000, some people are making over $1 million. Any questions on that before we keep moving? Okay, so I think it just takes some used to kind of going through some of these different models. The dividing or multiplying by 100 part, I think that's tough to keep track of. Like I said, if you can just think about it as, if I'm trying to go from percent to level, then I need to make sure that I'm dividing by 100, right? So that was my level log, because when the x variable is log, then I'm thinking about it's a 1% change in x. So anytime I'm doing that, going from a percent change to what's the predicted unit change, I'm going from percents to units. The level log, I divide by 100. If I'm going from units to percentages, I need to like go from decimal form to percentages. So if I have a log level where I'm looking at unit changes in x, and then what that predicted change, percentage change in y would be, going from levels to percentages, that's where I multiply my coefficient by 100. And the other two, I don't have to do anything. So those are nice, right? Level models and log models should be a lot easier to interpret, right? And that's probably the ones I would focus on the exam. Not requiring you to kind of remember that you had to, when you have to multiply or divide by 100, because in practice, even if you forget, you can always look it up, right? So I mean, that one's a little bit less important, but I do want you to be able to kind of do the interpretations for logs and level models. Okay. So those are kind of the two Excel examples. I mean, really the Excel at this point, it's just using that regression tool. The next thing I want to think about, and here I think I've got a real goofy one. I think I had like a bluegill data set, and I just thought that was bizarre, and so I wanted to use it. But maybe just looking at these different combinations of like logs and levels, that's one way of getting at non-linear relationships. The second way is we can actually allow for a quadratic relationship, okay? So what we can do is, instead of running this simple linear regression where x is just continuous, maybe I'm thinking about y is the length of a bluegill and x is its age in days. Right? Well, think about it like in terms of a human, right? How much do you grow when you go from like, I don't know, 12 to 13? It's going to be a lot more than when you go from 40 to 41. Probably 40 to 41, there's probably going to be zero change in here, not length, right, of a human, but I guess height of a human, okay? And so we know that like when it comes to any type of progression, like early on in any animal's life, right, it's going to be much higher rate than it is towards the end. So we know that if we're just looking at the relationship between age and length of this fish, it probably isn't going to be linear. It's probably going to look something like, if I was like thinking about drawing this out ahead of time. So here's the age, here's length. I would probably think initially, maybe only a couple that being a day or two older predicts that length goes up by a lot, right? When fish are real little, they grow real quick. And then over time, it starts to slow down to a point where like after the first, I don't even know what it is. I don't know enough about fish, but after like the first year, right, after the first 365 days, my guess is the fish doesn't grow near as much, or you know, almost flatline its kind of growth. I want to think about this like a human. Right? So we know it probably doesn't have a linear relationship. So if I try to make predictions, like if I'm thinking about the data here, the data probably looks something like this. Well, if I try to use just a linear line to pick up this relationship, so let's say I try to just run my simple linear regression, my line of best fit might be something like this. Well, I'm going to be making really big errors. Now, I minimize the sum of my squared errors using that approach, but the linear approach will still be making lots of errors. So what do I want to allow for? Some curvature here. So instead of thinking about a relationship like this, what we're now going to allow is for a relationship like this. Right? We're going to include a quadratic term where for us, our x variable, this would be age. So we'll throw in this additional control variable, which is age squared. Now, when I'm making predictions, it gets a little bit harder because a 1 unit change in x, well, that's actually going to have two effects, right? It's going to change y through this variable, because if x goes up by 1, x squared has to go up. Right? And it's also going to change my predicted y variable from that coefficient of b as well. So it's almost like I have like two coefficients that are related to the same variable, which is age of the fish. Now, the one's really picking up kind of what that kind of rate is, right? Is it increasing at an increasing rate or increasing at a decreasing rate? Like my squared term kind of tells me whether or not that relationship is like convex or concave. But the interpretation of just a 1 unit change in age will become a little more complicated, and we'll talk about that here in a second. But this is a general idea of what I'm doing, right? I'm adding in this quadratic term to allow for my line of best fit to fit a relationship that's not linear, to better fit the data. So if I'm thinking about this right, if I run just the simple naive one where I just treat it as linear, probably positive, right? I would think that as a fish gets older, it's going to grow in length. So we look at this, sure enough, right? I don't remember the units that they measure these fish in either. I should have looked this up because it's clearly not like centimeters or something. It's like a very small unit of measurement that maybe it's millimeters. For the sake of the example, we'll say it's millimeters. So for every day older a fish gets, it goes up by 22 millimeters in length. Right? The R squared is pretty high. The age of a fish tells you a lot about its length, apparently. We're explaining 73% of the variation that exists in that length variable just by using the fish's age. And if I look at that p-value, it's pretty much what? Yeah, e to the negative anything means you basically have a p-value of 0. Right? You're moving that decimal place a lot of places to the left. So, we already talked about why we would think this is probably not a linear relationship. So let's throw in this quadratic term. Let's throw in this age squared term. Okay. Well, now, if I rerun this regression, right, it allows for there to be some curvature to a relationship between my x and y variable, or the length of the fish and its age. So going back maybe to some like calculus kind of stuff that you probably don't want to deal with or you want to forget, right? When we're looking at kind of the coefficient on the non-squared term, right? This is going to tell us about like whether or not the relationship between our x and y variable is positive or negative, right? This will tell us that as age goes up, length of the fish also goes up, or if it was negative, as the age of the fish goes up, the length goes down. That doesn't really make sense in the context of this example. We know it's going to be positive, right? However, maybe that increase in length is occurring at an increasing or decreasing rate, right? So here, if I also have a positive coefficient on my squared term, that's telling me that as x is increasing, it's increasing at an increasing rate, right? So if I go like a 1 unit change here, well, my predicted y didn't change much at all. Whereas if I do like a 1 unit change here, my y has gone up quite a bit. So if they're both positive, it's telling me like it's increasing at an increasing rate. And then if it was negative and positive, it's decreasing at an increasing rate. What if I've got a positive and a negative? Well, that's telling me that, if we think about here, initially this x variable, right? It's increasing. So if I go up 1 unit, increases quite a bit. But then as x continues to get larger and larger, if I go up that same unit, y didn't change much at all. So here it's kind of increasing at a decreasing rate. Okay. And really, I should have, you can kind of think about it this way. What we're picking up when we're making these predictions, I can use the same thing, is really going to be when we look at the actual data, it's not very likely that the actual data is a full quadratic, right? It's not like the data is going to look like this, to where I'm going to see like this line of best fit going through. There's not many things in the world that have those there are some, but like most of the time, what we're really looking at is like, yeah, this, right, eventually goes back down. It just starts going back down at ages that we never see in the data, right? Like we're only going to probably be seeing like half of that quadratic in the actual observations. But using this quadratic term still allows us to capture kind of what those relationships are. So if I run this regression, let me see, there it is. And I guess if we think about here, I should have paused here. We know the relationship between age and length is probably positive. But what about kind of this age squared? Well, we think that it probably looks something like this, where it's increasing at a decreasing rate. So if I had to guess, I would probably guess the coefficient on my squared term is negative here, right? Just intuitively what I would think about the growth of fish or the growth of any animal. But we run the regression, and sure enough, our kind of thoughts are supported, where we've got this positive relationship that exists between age and the length of the fish. But every unit increase in age, right, as we get to higher and higher ages, right, that increase is happening at a lower rate, right? Or it's increasing at a decreasing rate. Okay. If I look at the p-value, they're both highly positive. So one of the things that you can do when you're adding in these square terms, just like with the log-log models, what percent of the variation am I explaining here? 80%. How much was I explaining when I just kept it linear? 73. So here adding the quadratic term seems like it's probably more accurately captures that relationship, right? It increased the R squared. Now, the tough thing is adding in a squared term, you're adding in additional controls. It sometimes will artificially boost the R squared. That's an issue that we're going to punt on for this class. We're not doing it in this class. Something maybe like an advanced stats you would learn, which is, I think it's 321. But what we can do to determine whether or not, okay, not just using or relying on the R squared, but did I really need a squared term here, is I look at this p-value, right? Because if that p-value was not really small, remember, every single time that when I was thinking about like the coefficient on the squared term, for every hypothesis, we're assuming that our coefficients are equal to 0. So if I end up with like a p-value of 0.3, that's not going to be less than any alpha I choose. I fail to reject that there's any quadratic relationship between these two variables, right? So if my p-value starts to get too high, when I'm thinking about the coefficient on my squared term, what that's telling me is that the relationship with these two variables isn't actually quadratic, right? Because that quadratic slope or quadratic coefficient value, I actually can't say that it's anything different from 0. Right? So I can use that p-value on my quadratic term to determine whether or not I really needed to look at that relationship or treat it as quadratic. If it has a really high p-value, I can't say that relationship between the quadratic term and my y variable is anything other than 0, which is basically just telling me that it's more likely the relationship is just linear, right? Because I didn't pick up any significance on that quadratic term. Now, for this stupid bluegill example, which once again, I don't know why I chose it, that's not true. I can actually reject the null here with very high levels of confidence. So here's an example where I could say, well, look, based off of this regression, I mean, this relationship definitely is not linear because my quadratic term is significant, right? It's telling me that there's definitely, right, a coefficient here that's not equal to 0. Questions on that? Is that making sense so far? 6 minutes. I think I want to do one more thing, which is our coefficient interpretation gets a little bit trickier here, right? But if you think about this in terms of like, I forget, hopefully I matched this up to how I wrote on the slide, but we think about a regression here. When I was thinking about the 1 unit change in X, would cause the predicted y to change by whatever my coefficient b was. What I'm really doing there is like taking a derivative of x or of y in respect to x, right? So if I think about, I think I wrote this as, I think it's beta 1 and beta 2 is how I did this on the slide. So instead of a and or b, I was using betas. So now if I think about the change in y from a change in x, what's that going to be? Well, I'm taking a derivative of this function. Beta 1 plus 2 comes out front. Now my marginal effect, right, depends on what values of x I'm looking at. So the effect of one unit changes in x will be different depending on what level of x I'm looking at. Right? If I'm at a value of x of 100 versus 1,000 or whatever it is. Right? So our marginal effect becomes beta 1 plus 2 times beta 2, or the coefficient on that quadratic term, 2 times that coefficient on the quadratic term. And then at different levels of x, the marginal effect of 1 unit changes will be different. Okay? So I can't really say there's not a universal marginal effect here. Before it was always just the coefficient, right? B or beta 1. Now I'm going to have to map out what the marginal effect is of what 1 unit changes would look like across all the values of x. Okay? So I think I have an example. If I use that GPA data that we had, and I include that quadratic term on the SAT score, right? Oops. So maybe initially I would think, that as I'm getting higher SAT scores, it's probably gonna be positive. I honestly don't know what the quadratic terms will look like. My guess is it would be negative, like just that, like as you start to get to like anything over a 1,500, all those kids are, all those students are going to be probably successful in college, and so they're not going to see as much variation in their GPAs. We run it, and sure enough, I'm wrong. So it actually looks like there's a negative relationship between SAT scores and GPAs. This is where you have to remember, well, what ranges are we looking at here? We're never seeing something from 0 to 800. So we're going to have kind of a weird interpretation initially if we just look at these coefficients. But if we then plotted them out, so all I'm going to do is plot out what the effect of a 1 unit change in SAT scores would be for different levels of, and GPA would be for different levels of the SAT score, right? Because I know that the effect will be beta 1. No, this is not what I want. Do I not have the marginal effect graph? All right, well, I guess I don't. I'll save that for next class then. So I'll bring that in next class. This was actually something completely different I wanted to talk about. So once we have these coefficients, we can use this marginal effect equation that we know, and we can actually map out what that marginal effect looks like across different levels of your SAT score. So I'll probably re-upload that, I think what I call it, GPA regression or something. I'm going to re-upload that file so that it has more worksheets in it, and we'll use those on Wednesday to kind of think about how do we map out these marginal effects when we want to get at these relationships that we think are nonlinear. Okay. Other than that, you've got that third individual assignment you can start working on. That a lot of the log stuff from today would apply to that, so that's why I wanted to kind of jump around a little bit. And other than that, I will not have office hours this Thursday. I'm going to be away from the building. So tomorrow, if you want to stop by anytime between 11 and 3, I'll have another 2 hours on there. I'll be here during that time block the entire time. Excuse me. So, but no office hours on Thursday. Okay. All right. We will see you guys on Wednesday.